Identifying IMFs in a substance. Week 2, Lecture 1. What do IMFs or intermolecular forces do in a substance? IMFs help keep a substance together in different forms of matter. These different states of matter have different appearances of their molecules. In some phases of matter, the molecules are orderly, and in others they're mixed and moving. Substances with stronger intermolecular forces are harder to break apart and cause them to shift phases. A liquid with stronger IMFs will take more time to evaporate than a liquid with weak IMFs. How do molecules look in a substance? The three main states of matter have distinct amounts of motion and an appearance of their molecules. First, on the left, we have solids. These molecules wiggle in place. They have fixed volume and shape. Liquids in the middle. These molecules move freely, but always in contact. They have a fixed volume, but not a fixed shape. Lastly, to the right, gas. These molecules do not even touch. They have no fixed volume or shape, but they may fill their containers. How do we find the IMFs of a substance? The IMFs, or intermolecular forces of a substance, can be determined based on the elements that make up the substance and how many total atoms are in the substance. Here is a flowchart to help find the IMFs for different substances. This flowchart is a series of questions to ask yourself while looking at a compound and select the available answers until you reach an endpoint where you find the IMFs of the substance. How does the flowchart work? If you've never seen a flowchart before, it is a list of steps for a process that has many different outcomes or results. In this case, it's meant to help us determine which of these three IMFs are present in the substance. To use the flowchart, begin at the top where it says Start Here, and ask yourself the question in the box for the substance you're looking at. Select the answer that best fits the molecule and continue by following the arrow for that answer. Ask yourself the question or do the action specified in the box and continue following the arrows. When you reach a box with no arrows leaving it, you have found the IMF of the substance. These will either be London dispersion forces, dipole-dipole forces, or hydrogen bonds. What can we do with this? By finding the IMFs of different substances, we can predict their relative IMF strengths. Which one is strongest? We can predict which will have the higher boiling point or the higher melting point. The substance with the stronger IMFs will likely have a higher boiling point and melting point. This also means that it will take longer for the substance to evaporate if it is a liquid. This is especially relevant for household items like perfumes or colognes. At home IMFs. Here is a small activity you could do at home to see how IMF strength is used in different products. You will need 2 paper towels, perfume or body spray, and a squirt bottle filled with water. What to do? Fold the water or the paper towel over 2 times. Spray 1 paper towel with perfume or body spray 3 times and spray the second with water 3 times. Let it sit for about 3 minutes. Come back and check the wetness and smell of the 2 paper towels. What's happening? The IMFs of the perfume and the water are not the same. Perfume is mostly made of chemicals without dipoles, so they have London dispersion forces as their primary IMF. Water, on the other hand, is made of hydrogen and oxygen, so its primary IMF is hydrogen bonds, the strongest of the IMFs. This causes the perfume to evaporate faster, so it smells more than the paper towel and is less wet than the water one. IMF strengths. Usually, the different IMFs fall into a hierarchy of their strength. Hydrogen bonds will be the strongest, dipole-dipole forces are second, and London dispersion forces are the weakest. This order can be broken down though depending on the specific substance being studied. For class, Use this order to assess which substance has stronger IMFs when comparing substances. Let's take a look at these compounds and find the IMFs using the flowchart. For methane, methane is CH4. It therefore has more than 3 atoms. Are there 4 of the same element present? Yes. So it is London dispersion forces, as we see here. H2S has 3 or more atoms. So we're going to go over here. Are there 4 of the same element present? That would be a no. Is H and then N, O, or F present in the compound? It just needs to be one of the 3 and H. We've got S and we've got H, so that would be a no. So it's dipole-dipole forces, as we see here. F2 would go to the left because we've got 2 atoms. Are these 2 atoms the same? Yes. So we've got London dispersion forces, as we can see here. And then CH2O, the C is 1 atom, the H2 is 2 atoms, and the O is another one. So there's 4. So there's more than 3 atoms present. Are there 4 of the same element present? That's a no. Is H and then N and O or F present? So we've got H and we've got O. Yes, so it's a hydrogen bond. Oh, my bad. Okay, there we go. Hydrogen bond. All right, we're going to try now find the IMFs of these groups of elements and arrange them from strongest to weakest IMFs. Remember that the strongest one is hydrogen followed by dipole-dipole, and the weakest is London dispersion forces. So we're going to start with Cl2. Cl2 is most likely London dispersion forces because if we use the flow chart, we will see that Cl is present twice. So there's 2 atoms and they're both the same. So it's London dispersion forces. NH3 is 4 atoms. So that's 3 or more. Are there 4 of the same? No. Is H and then N and O? Yes, right? Because we've got 3 H's and 1 N. So it's a hydrogen bond. So that one is going to be the strongest. And then HBr, apologize for going back and forth. HBr has 2 atoms. Are they the same? No. Find the EN difference. Okay. For this part, what you need to do is go to the electronegativity periodic table that I have in week 1 and find the difference. And it doesn't matter if you have a negative amount. That negative turns into a positive, right? So BR is close to F, so it's going to be like 3 point something. H is going to be 2, so it's going to be between Cl and NH3. Are H and F present? No, so it's dipole-dipole. Okay, off to the second one. CH2Br2. This is going to be 2 atoms plus 2 atoms is 4 plus another one is 5. Okay, so we've got, are there 4 of the same element? No. Is H and then N, O, or F present? We've got C, we've got H2, and we've got Br2. So no, that's a no. So it's going to be dipole-dipole. Okay, and then HF is 2 atoms. They're not the same. Find the EN difference, so 2. So it's going to be more than 0.7. Are H and F present? Yes, so it's a hydrogen bond. So that's going to be the strongest one. So that's why it's far to the left. And then CBr4, that's 5 atoms. So we're going to go over here. Are 4 of the same present? Yes. So it's London dispersion forces. So that's the weakest one. And then the last question, we've got H2O, ClBr, and H3P. So let's start with water. Water has 3 atoms, so it's going to be over here. Are there 4 of the same element present? No. Is H and then N and O or F present? Yes, right? Because we've got H and then we've got O. So it's a hydrogen bond. So that one's going to be the strongest. Cl and Br. Cl and Br, those are 2 atoms. Are they the same? They are not the same. Find the En difference. Cl and Br, those are going to be under 0.7, so it's London dispersion force. That's what's over here, the weakest. And then H3P. Okay, H3P, that's 4 atoms. Are there 4 of the same? No. Is H and then N, O, or F present? That's no. So it's going to be dipole-dipole. That is why it's the intermediate strength force. So as you can see here, H2O is the strongest, H3P, which is dipole-dipole, is in the middle, and then the weakest, ClBr, is over here with London dispersion forces. All right, kiddos, so that is how the flow chart works. Good luck during week 2.